Hi everybody, Dr. Kirkvold here. We're doing Engineering 314, Materials and Mechanics, and this video I'm going to do an example problem of how to construct a shear and moment diagram. So let's get started. First of all, we can determine moment and shear at any section of a beam. So let's start with this example. We have a simply supported beam with two nodes, its length 3 feet, and I've put a uniform distributed load, W of X, and that's 1 kip per foot. We have our beam with nodes A and B. We can replace our end conditions with AX, AY, and BY as shown, provide the global coordinate system. And we have our external load, W, as a function of X equals 1 kip per foot. When we do equilibrium with a distributed load, we can find our equivalent load. Now we start with our equations of equilibrium. Sum of forces in the x direction is a trivial solution, and we get AX equals 0. Next, let's do sum of moments, and I'm going to choose to do them about point A. So we get BY times 3 feet, positive moment, minus 3K, the FEQ, times 1.5 feet, and that equals 0. We can solve for BY. We simply move one term over and divide by 3. We can check our terms, do a unit analysis, and it gives us kips. That makes us feel good. And so we end up with 1.5 kips. Let's do sum of moments in the y direction. We have 3 different forces acting in the y direction. We have our FEQ, AY, and BY. We know both FEQ and BY, so AY is our only unknown. Solving for AY, we get AY equals 1.5 kips. Note that's equal to BY because the beam is symmetric. So let's start over with our beam and give us some space to work. Remember how we started this off by saying we can make a cut and find the shear and the moment at any section. So let's do that. Let's start by cutting it at, say, L equals 1. We have to add shear and moment on the cut surface to cause the entire segment to be in equilibrium. I follow my positive sign convention, and I can label those as V1 and M1. Now let's determine the shear and moment. We'll start with summing forces in the y direction. This is relatively easy. We have our 1.5 kips, and we have our W sub x multiplied by the length of that little member. That's our length, where x equals 1. And V is our one unknown. So our V sub 1, which is essentially shear as a function of X, canceling everything out, we get 0.5 kips. It's a positive value, indicating we have it in the right direction. But this is our equation. And we're going to do sum of moments about the cut face, A sub y over here, the 1.5 kip. So we need to calculate our FEQ. And we get a value of FEQ equals 1 kip. It's located at half the distance, which is x equals 0.5 feet. Now we're going to sum moments. When we do this, we're going to do it about the cut face. So it's about the node where x equals 1. That's why I'm going to call it M1. 1.0 kip feet, M1. We can do this again at any section, so let's pick x equals 1.5. It might make sense for us to go ahead and tabulate the values that we just completed. And so we can get started with cutting the beam. You'll notice that I labeled the shear in the moment as shear sub 1.5 and M sub 1.5 to indicate the value of X. Summing moments about the cut surface. we get m of 1.5 equal to 1.125 kip feet. And again, for sum of forces in the y, we have 1.5 kips minus v of 1.5 and minus 1.5 kips, the FEQ. And we get v of 1.5 equal to 0. So I've added these to my table up here, and we can think about another cut. We could do a cut at x equals 2 feet. To speed this along a little bit, we can get m2 equals 1 kip foot, and v2 is negative 0.5 kips. That negative means it's in the opposite direction that we assumed, so it's actually going up. Let's add those values to our chart. If we can cut it at any x, we can also draw a plot of the shear and moment. And I'm going to plot v as a function of x along the length of the beam, directly under the beam. Plot my points. I am noting the specific value. I also have my units. We can do the same thing for moment. M as a function of x in kip feet. Now I want to indicate my values, especially for this one. And these are at 1.0. Now, to get the complete graph, we could keep cutting sections, but I'm going to get tired of that real quick. So why don't we do this in general and come up with an equation that we can plot rather than doing individual points? So let's do that. We're going to go ahead and cut the beam at x. Now, let's go ahead and do equilibrium the same way we have always done. We'll start with FEQ. Okay, FEQ is equal to our 1 kip per foot times our x feet. So notice that FEQ is now a function of x. The location of FEQ is simply x divided by 2. The sum of our moments about the cut surface x, we'll have our m sub x, the value of FEQ, it's a function, and then we have the distance from the cut face to the FEQ, which is also x over 2, and that's in feet. So we're staying consistent with our units, and of course we have our 1.5 kips times the distance, x feet. All that equals 0. Solving for mx, which is essentially m as a function of x, we get 1.5x minus x squared over 2. You'll notice that this is a second order equation. We can do the same thing for shear. V sub x going down minus x, which is our FEQ, and our positive 1.5 kips, solving for v as a function of x. So we'll get 1.5 minus x. Units are kips. And we have our equation for v. Now notice, these are all in terms of x. We can plot these along the length of the entire beam. Okay, so I have indicated my maximum and the maximums here for shear moment as well. I want to teach us a little bit of housekeeping. So I'm going to indicate that as a positive area and this as a negative area, and draw a miniature version of the shape of that beam. So to summarize, the first thing we did was we had a beam and we found the reactions in equilibrium. We knew that we could take a cut at any location. So we took a cut, non-specific location x, and we did equilibrium for this condition. That produces for us equations for the shear and moment diagrams. We can then plot the shear and moment diagrams and note that the extreme values, maximums or minimums, that we need to consider for design. Now let's write this out explicitly. As our method is, first, we solve for the reactions. Second, we set up our coordinate system. Third, we're going to section the beam wherever load changes. When I say where the load changes, we haven't talked anything about that yet. So really, I don't like that wording. What I would like us to say, at locations of interest. The fourth, we're going to calculate the general moment and shear equations. We will do this for each segment of interest. You'll note that this segment of interest will be tied to the locations of interest. Finally, we're going to plot. I want to make sure that there are, housekeeping items that we don't forget. So I'm going to things we must include. Show your coordinate system. And finally, for the plots, if the plot is linear, I want to see both points and the line. And if the plot is parabolic, I want to see the end values and the end and the maximum or minimum values. I hope this gives us a strategy and a place that you can come back to. Thanks for listening.